Okay. Alrighty. Module 6 is open. It's lacking some things. And I still need to get a quiz going for you for Module 5. And it's only going to get worse, so, I mean, for me, so. Let's see. Any questions on anything right now? You just have a burning desire to know? Yeah, I'm going to go with a no on that. All righty. Okay, so we are, as I say, getting into Module 6, which is Chapter 5. And so again, as we look at this basic question of dependency, you know, it does something depend on something else, right? You know, can we get information? You know, can I look at item A, and then does that help me somehow in predicting item B? Okay, and that's the question that, you know, often in statistics, that's what we want to know. Okay, so for instance, big thing right now, right, is a vaccine, and the question becomes simply, does this vaccine seem to have any impact on any given disease, so COVID-19, right? And what you want to be able to say is, if I know a person was vaccinated, I will predict they are way less likely to get COVID-19. That's one thing you would like to say. Another thing you would like to say is, oh, you know, if this person gets vaccinated, there are no weird side effects. Now, I don't want to help anybody who's an anti-vaxxer. I hope there are none here, because this is science stuff. But, you know, any vaccine does carry a risk. Okay, the flu shot one gets, it uses a protein, I don't know, similar to eggs. I don't know if it's exactly eggs, but so if you are allergic to eggs, you have a problem in trying to get a flu shot. So, you know, any vaccine can have complications, not necessarily because of the what it's trying to prevent, but because of how it can get delivered. Okay, so, you know, there's that question. If I know a person has gotten the vaccine, actually there's a case where you hope it's independent. Right? If I know you've gotten the vaccine, I would hope to say, you know, that doesn't help me to predict whether you're going to have any of these particular other things. Okay, so there are cases where we don't want to reject H0. We do want things to be independent. Okay, and you know, so as we look at this stuff, that's what you want to pay attention to. And so again, we have our response. And this time, since we're going to start into regression, I will put our explanatory or predictor down here. Okay. Now, again, I want to look at the chapters, and so we started with our response variable was categorical. And then we moved to numerical. In our explanatory variable, we started with categorical. And then we move, now are moving to numerical. This was chapter 3. Okay, and the big thing we used there was chi-square, test of independence. Then we moved to chapter 4. And we were using the ANOVA, analysis of variance. And now we are in chapter 5, and this is regression. Typically, you'd say linear regression. For us, it's pretty much all we're going to do anyway. So that's where we are. Again, these are always the same question. And something, after looking at the projects from 3 and 4, I think something very important for you to keep in mind is for every single one of these tests, one way to state the null hypothesis is the two variables are independent. Every single time. Okay? All three of these items that we're looking at, all 3 chapters, what it boils down to is the null hypothesis says they are independent. I can't gather information about one by looking at the other. Okay, and so HA is the two variables are dependent. Okay, and again, something to add on here, our p-value, and again, you got to be careful. This stuff's all based on probability. Probability starts with a p. Proportion starts with a p. P-value, the reason it's called a p-value is it is a probability. Starts with p. All these words start with P. I don't know why. Maybe a different language would be better. Okay, and they wouldn't all start with P, but they all start with P. So you have to be really careful when you see something with a P. Okay, because again, I noticed in the projects, people, not everybody by any means, right? But people were confusing a proportion with the p-value. They are not the same thing. They both are certainly likelihoods. Okay, I mean they're based on the same idea, but they are not the same specific item that we're looking at. But here, typically for us, p-value is bigger than 0.05. A few people are getting that backwards still. And we're going to go here, p-value less than 0.05. And again, the whole idea is what is a p-value? All it's telling us is, right? So the p-value, if H0 is true, okay, and it's always that. It is absolutely always based on your null hypothesis being true. And so if H0 is true, this gives us the probability of getting our data, and there are various ways to then add about the other stuff, because again, with all these, they're based on the normal distribution. So if you truly said, what's the probability of getting exactly my data? The answer is always 0. Okay, so to stop here is definitely not technically correct, so we won't stop there. Okay, but that's the idea. I mean, you know, if you can just carry that with you, that it's kind of the idea of if H0 is true, if we're actually pulling things from something that's independent, two populations here, well, yeah, we'll go with two, since they're two random variables. Two populations that are independent, if we're really doing that, how likely could we have seen our particular data? Now, but again, it's our data or something more dependent. Now, there are other ways to say it's something more extreme. Okay, because when you think of a null hypothesis, you tend to think of a distribution, and so you have a population mean, and our data are always away from that mean, and so the question would be, well, how likely could we get our data that far away from the mean, or even further? Okay, so that would be an extreme idea. But in terms of these tests, well, we're basically asking about, okay, could we get our data or something that looked even more dependent? Right? You know, our data or something that even looked sort of worse from the standpoint of the null hypothesis. Okay, and again, going just to make sure we've got this idea, and you know, and I think it's very important that we try to realize it is exactly this same idea that was here, here, and is now here. Nothing's changed. The only thing that's different is the style of data or the type of data. And so, well, we have to use a different test. That's all that's happening. Different type of data, so we have to use a different test. And so, you know, I think it's probably easiest to see the dependency in just a 2x2 grid. You know, so here's variable 1, and it's got at least 2 possibilities. Otherwise, it's not a variable. Right? I mean, you know, if I tell everybody, hey, you've got your choice of ice cream, you can have vanilla. That's not really a choice, right? You know, so there's no variable. So here we got variable 1. Here's variable 2, and you know, this could be A and B, and then this could be A and B of some sort of categories. And so something that is perfectly independent, you know, it might be something like, okay, I had 10 observations there, 20 observations there, 30 observations there, and 60 observations there. And this is independent because as I look at this, if I look across here, it would say this A here happens a third of the time, right? 10 out of 30, because there's 10 and 20. So 10 out of 30. This happens a third of the time. But if I look down here, it also happens a third of the time, because it's 30 out of 90. So if I tell you, oh, you're in row A, great. Didn't help me a bit. I'm still going to go with, I think that happens a third of the time, that happens 2/3 of the time. I'm not going to change. It's perfectly independent. And if I have independent rows, well, that's one of those math things you can show, well, the columns are also, it has to work the same way. As I look down this way, this is 1/4, 10 out of 40. So this column had, it's 1/4. This one, it's 20 out of 80, so that's also 1/4. So if you tell me I'm in column A, I'm going to go, oh, well, I think the first row happens 1/4 of the time. If you tell me I'm in column B, I go, oh, great! Yeah, the first row happens 1/4 of the time. No difference. I get nothing from knowing which one I'm in. On the other hand, now, the question is it statistically significant dependence? I don't know, right? We'd have to do a test. But here, if all of a sudden I kind of switch this and I say, oh, that's 20, that's 10, and that's still 30, and that's 60, then all of a sudden, there's a big difference. Now, in either case, right, if you tell me I'm in this column, if I'm in the first column, I'm going to get, and somebody says, okay, I grabbed something out of the V1 hat, and I'm going to tell you it was this column. What are you going to guess? Well, I'm going to guess B, because there were 30 to 20 of them. Right? So I'm going to guess B. Now, if I know I was in this column, I'm still going to guess B. So my guess didn't change. However, the confidence in my guess changed a lot. Right? Here, this is 30 out of a total of 50, so about 60%. So 60 to 40%. I feel pretty good about that. Say I'm betting on it. I might wager a bit of money on that because the odds are forever in my favor, right? What's that book? And may the odds be in your favor. What the heck's? What's it? Oh yeah, Hunger Games. Yeah. I've seen the movie. Didn't read the books, but. Or movies, I guess I've seen. But, so, the odds here, they are in my favor if I go with B. But if you tell me I'm in column B, I might wager more money. Because now, right, it's 60 out of 70. And that's like, what is that? That's 80-some%, 85-ish%. So here, it was 60%. Well, that's pretty good. But all of a sudden here, 85%. There's probably a dependency, statistically speaking. But the question is, okay, if this actually came from something that was truly independent, if that was the case, how likely could I have gotten those data? I don't know. Okay, we would have to do a chi-square test to check that out. Okay, but we could do a chi-square test and see what's going on there. Okay, and by more dependent, I mean, let's make this, 21 and 9. Oh, that's even more extreme. 22 and 8. Oh, that's even more extreme. So this is looking at all those possibilities. Okay, but that is exactly what you're doing every single time you do this. Okay. Questions on anything? You don't really look like you want to ask questions, but You just never know. Okay. All right. So we are now into both variables being numerical. And so to see them visually, we can use a scatter plot. And generally speaking, on the x-axis, we put the explanatory. And on the y-axis, we put the response. And you often see the words of prediction much, much more when you're talking about numerical data like this. But again, it's the same idea when you go to the other. So here is explanatory and response. And what we're looking for in this case, and we've talked about this before, we are looking for some kind of sign that knowing something, usually you think of it as the explanatory variable, knowing something about this variable, I could tell you something different about the response variable. And so, if I see something like this, well, if I'm here, I would guess, something in there. And, but on the other hand, if I'm out here, if I know that's my explanatory variable, if that came up, then I would guess something between there and there. They look the same. I gained no information. Right? Nothing happened. And so, this is independent. On the other hand, if we have data doing something like this, okay, if we have that, then if you tell me, oh, I'm down here, well, then I would guess something in there. But if I'm up here with the explanatory variable, I would guess something in that range. Oh, I would guess something very different. Okay, so here we have dependent. Now, we're going to use a particular tool that in some ways is very, very limited. But in other ways, if you start looking at the modeling aspect of it, it's extremely flexible. Okay, now, so when we say it's limited, so we're going to look at this thing called linear regression. Okay, and it's in particular called linear because it is limited to looking at straight line dependence or independence, but in particular, we're trying to see if there's any dependencies. So that's pretty limiting. Now, the reason I say that is that, independent, right? Because I gain no information by knowing something about the explanatory variable. But now, suppose my data look like that. that's probably a cubic function. And if you just give me a function, well, if you tell me the x value, I can tell you exactly what the y value is. You can't get any better prediction than that. And that's awesome prediction, right? But when you have something like this, it's actually not going to do as well with our linear regression. Okay, it's not going to do as well as a straight line that, say you had some other data, I'll use some x's. Now you see here I pretty much made just a single curve. I mean that's perfect prediction. If I tell you this x value, you just go up there and tell me what the y value is. That's perfect. You can't get any better than that. Yet, most likely, if you were given these data that go along this straight line instead, but are a bit dispersed, these will probably do better at showing that dependence. Okay? Because this tool really is that limited. It is limited to looking at a straight line relationship. Okay, so, given x and y, two random variables, assuming the x is the explanatory, y is the response, our linear regression will examine the model the model y, and I'm going to use a tilde because when you're talking statistical models and that sort of thing, that's what statisticians tend to do. I'm going to pull up Desmos in a minute, and we'll use that tilde to do this. So y is explained by the model bx plus a. Now I could use beta and alpha because that's what most statisticians use, but I don't know, that might freak you out if I use Greek letters, I don't know. Maybe if we had fraternities and sororities, it'd be much better. So we're looking for a slope and a y-intercept. Okay, this is the modeling part, and so this is where actually things are just a little bit different in this chapter, in that there definitely is this model attached to the analysis. And in particular, what we do, we check the probability that B, that's a P, B is not equal to 0. The slope. That is our test. Okay, now we're going to look at other stuff that have to do with the model, this model. But the test, the thing that's like our chi-squared test or our analysis of variance test, what it's checking is simply that question. Okay, and And so the probability that it's not 0, well, really what's going on is the null hypothesis is that b equals 0. Okay, the slope of the data, the trend in there is 0. Now, think about that, right? That was this case. That's a slope of 0. Yeah, this variable is of no predictive quality for the y variable. Doesn't help me a bit, right? But then the alternate is that your slope is not 0. And that picture might look like, here's a negative slope. Might look like that. And well, sure, that helps me predict. Again, because if I've got small values of x, in this case, I would predict bigger values of y. If I have big values of x, I would tend to predict small values of y. My prediction changes. There's a dependency. And so it's all about the slope. We really don't care about the y-intercept as far as our test. Now, we're going to be doing some other things with this, and it's the modeling aspect that actually can help us out and make linear regression actually a very flexible tool. It always does the same thing. It's always just asking this question. And so we'll see we have to trick it, basically, and do some work with the modeling that way. But as long as we realize this is the hypothesis test that's going on, hopefully we're pretty safe. Okay, we keep that in mind as we do things. And so we'll get a p-value. And again, it's always under the assumption that the slope is 0. Well, how likely could I get data that look like this if the slope really is supposed to be 0? Oh, okay, well, that's our p-value. It's kind of that probability that it's not 0, right? And if that's below 0.05, we reject the null and we go with the alternate, that the slope's not 0. But again, like in your projects, the answer that the slope's not 0, who cares? What's that mean? Right? So what you really want to talk about is the dependency between those two variables. Or, the slope, we fail to reject the idea that the slope is 0. In other words, we don't have enough evidence to reject that. Fine. What the heck does that mean? Oh, well, right now the best we could say is that those two variables are independent. We don't have enough evidence to say they're dependent. We'll have to go with independent still. Okay, but what we're maybe trying to say is that they're dependent. And so we're stuck with that. Okay, so that's what we're doing. Now, and the way this model works, actually, it's a interesting model, I think, in that I have not looked carefully in a long, long time at the mathematics behind it, but the way you could think of it is, if I was just given some data, some x's and y's, and I wanted the simplest model possible, so the simplest model for the y data, because that's, again, what you're trying to think of as predicting, is that y data. The simplest model would be something like y is a constant. And actually, you know how to answer that question. Okay, because if you think about that, what we're saying is we've got a bunch of y data, even if you put it with the x data and so forth. And who knows, it could seem to have a trend or something like that, but we've got a bunch of y data. But we say we want the simplest model, and that would just be a constant. And actually, well, that constant, the best model, well, think about it. You take a bunch of data, and somebody says, what does your data say? What do? Right? You get a bunch of data. You're in a biology class, right, or a chemistry class. They give you a bunch of data. You plot it usually, I guess. But what else do you do? Almost every time they give you data, what do they want you to do? Nothing. Yeah, I wouldn't want you to do anything. Now, what do they want you to do? Oh, you can speak? Really? If we listen really carefully over there, she might tell us. Luke, you're first on the list. What do you have to do? You're given a bunch of data. What are you usually told to do?
Find some values like average.
Yeah, there you go. They say, oh, find the average. Well, why would you do that? Actually, if you're going to go with a simple model, what a great model, right? The average is going to be somewhere in there, y bar. Right? And if I just had to pick a single number, sure, looks good. It's in the middle. Looks like a good idea. Now, it's interesting, though, that what happens when we go to the model plus some slope times x, that the answer to this always, using least squares criterion and all that, always, if I also went here and I found x bar, this answer, oops, I missed. Okay, there we go. Always goes through that point. Which is kind of interesting, right? So in a way, it's like it builds on that original simplest model. And so this answer, when you find it using technology, something like that, if you were to find the average of the y's, the average of the x's, and check that, it will be on that line. And so, in some ways, that can kind of take some of the mystery out of it, is you kind of go, well, in a way, that sort of makes sense, right? Is I want to know, in the end, right, I want to know whether that is 0 or not. What might I do? Well, I might go to the middle of all my data, x bar, y bar, go to the middle, and kind of look at a line and ask myself, does it look like that line, as I look at the data, should sort of balance straight across, or should it tip one way or the other as I look at the middle? And, you kind of look at it that way, you go, oh, yeah, sure, that might be a reasonable way to attack this. And actually, the calculations, the mathematics, in essence, that's what they do. They kind of go to the middle and then play with the slope to do the least squares idea. And the least squares, all that's doing, I think the only truly important part for a class like this with the least squares criterion idea is that it has a direction. Okay, so the least squares criterion is measuring those distances and squaring them. That's least squares. Squaring those distances and finding the line that minimizes the sum total of those distances. Now, in the end, why is that important? Well, what I think is important is for you to realize that, okay, I do that, there's x and there's y. Now, if for some reason I swap them, I don't necessarily get the same answer. Right? What you might think is if I end up with y equals bx plus a here, well then I should be able to solve for x, right? And I'd have y minus a equals b times x, divide both sides by b, and I could write x equals y minus a over b, like that. Most likely, it's not the same line you would get here. So if you replotted the data and had your data there and you found that best straight line, it probably wouldn't be exactly that one. Okay, so here you would have x equals, and now I'll use a b1 y plus a1, but most likely, so here you see the slope is 1 over b. Most likely b1 is not exactly equal to 1 over b. It's probably really close, but it's not equal. And I suppose if you worked hard enough with the data, you could get them pretty far off. Not sure. And then similarly, A1 is not equal to minus A over B. Okay? It's a different. And the reason it's different is that these are going parallel to the y-axis here, and here they're going parallel to the x-axis, and those are slightly different. Now, there is actually a statistical technique called, where they do, what the heck do they call that? Overall squares, minimizing the overall squares. But in that case, they minimize the perpendicular distance to the line. That actually would work in either direction. Okay, but these do not work quite in the same direction. Well, actually, a good example to show that you get very different things is all you have to do is do just a very symmetrical cloud of data like this. If this is x and y, you're going to get that line. Okay? But if you do it as y and x, and again, suppose you have very, very symmetrical data, so it looks almost the same, you're going to get that line. But think about it, right? Here, if the slope is 0, in mathematics, you would say, oh, this should be a vertical line. It's not. Okay? So you get very, very far away from this if you have the right data. Okay, so that's just, to me, that's what you want to be careful of, though, is it really does matter which one's the explanatory and which one's the response in terms of the model and the analysis and so forth. This really does assume one particular direction. Chi-square, it didn't matter whatsoever. Okay, columns, rows, interchangeable. Didn't matter. Does here. Okay, so you can get two very different answers when you do that. Okay, well, so I want to show you a little bit with Desmos here. partly just to show that decimals can, if you give decimals data, it can do a linear regression for you, just like that. So what I did was I plotted two different curves, 2x plus 3, so the straight line there in black, and 2x squared plus 3, the parabola in red. And then I made data from that. So I just picked some x values, -3 to 3, and found, and just created some data. So it's perfect data. It goes right along the straight line. So there's F1 is the linear, F2 is the quadratic, and if I click on that to show the points, you can see the dots show up, and so there's the data. Similarly here, I can get the dots to show up, and there are my data. Now, what happens if I do that model? So I said I made a new list called Y1, where essentially I'm just making that list again. It turns out that Desmos doesn't really like you to use something like f of x over here in the y part. So I figured that out when it didn't seem to like it very much. I mean, it still did something, but it wasn't quite what I expected. So here's that model, that the y values are explained by some slope times x plus a y-intercept. And now here it's giving this thing called an r-squared. The r-squared can go between 0 and 1. 1 is great. It means that the model explained all the variation in the data. That's what we want as far as a model. We want ones. That's a 1. It should be, because I gave it a function, right? I gave it that function. And it did indeed find that the slope was 2, the y-intercept was 3, which is what we had here. Okay, now, here's the drawback from the linearity standpoint. Okay, here's this data. That data, I can predict y perfectly from x. Perfectly. Yet, if I do that same thing, I make this list y2s here, out of those, the 21 and so forth, the 2x squared plus 3, what happens is, oops, where is it? I get 0 for explanation. Now, let's kind of see these. So this will plot the best fitting curve. Now, that went fast, right? So that black line turned to blue when I clicked the blue. So it predicted exactly that line. Okay, the problem is here, it wants to predict a straight line for those data. It predicts a horizontal line, which says, well, the slope is 0, and it fits the data horribly. Okay, because remember, here are the data. That looks terrible. Okay, and if we looked at a p-value for the slope, I'm sure it would say a huge p-value, so we would go with a slope of 0 and independent. Yet, it's obvious that there's a dependency. I can predict perfectly, so there is a dependency. Yet, this method would not show that. Now, where it's amazingly flexible is actually I can fix it by tricking it. Okay, so what I did was I made a column called x1 squared, right? Because if I renamed this x squared here, if I renamed it another variable like m, now probably not m because then you'd think it's slope, right? Z. If I renamed it z, it would look like 2z plus 3. That looks just like 2x plus 3. Perfect. And so if I ask it to create that model. So here I'm saying let x2 be the x1 squareds. So I'm tricking it. I'm making my data into this x squared. So instead of using my raw data of the x1s, I'm going to use these transform data because if I use those data, it should look like a straight line in those data. Does that make sense? Right? Because if you think of it as z, it's just 2z plus 3. Well, so if you do that, here I did it, and now that's a red line, and it went there. So if I get rid of some of these others, get rid of that original one up here. So you see, right, that model, it just went back with that straight line. Because as far as it's concerned, it is dealing with 2x plus 3. It doesn't know any different. I tricked it by giving it the x squareds instead of the x's. And then it does it perfectly and comes up with the multiplier. I won't call it the slope because it's times x squared, but the multiplier, 2, and then the y-intercept of 3, exactly how the data were generated. Okay, so that makes this extremely flexible. If we can trick the model to thinking it's working with a straight line, we can do all kinds of stuff. You can fit all sorts of data. But you have to realize, how you want to transform that data. Okie doke. Questions on that? All righty. So go ahead and get started on 6. I'll get the project taken care of here very soon, I hope, and get quizzes going for you. And I will see you next Tuesday.